And welcome back. Today we will continue on with where we left off with our discussion of the network layer. Administratively, before we get started, we have homework 3, which has been posted on the course Blackboard. This is a number of questions about the transport layer. It is due on the 31st of March, a Tuesday, 2020. That is a week from this past Tuesday. And it will be due at the usual 11:59 and 59 seconds p.m. That's 1 second before midnight. Please make sure you are looking at it and going through those questions. So where we last left off, we talked about IP fragmentation. And in our story about IP fragmentation, we talked about so-called media transfer unit as the maximum transfer size for some particular link. Now, of course, depending on the type of link you're using, whether it's wireless or wired, satellite, so forth, you're going to have a different MTU. So then what happens if from one hop to the next, you traverse a link with a larger MTU, and then on the second hop or link along some path between two communicating endpoints, the next MTU you encounter for that next link is smaller? Well, what happens in the network layer, specifically in IP, Internet Protocol, it divides that datagram of the larger MTU up into smaller pieces called fragments. And these fragments are forwarded along, and they're not reassembled into the original MTU or the original data until it reaches the endpoint. So here we have a datagram that goes from that top or left-hand router here, and that datagram goes to this next router along a link, and that link has a particular MTU or datagram size. And it's broken up into pieces, in this case, 3 smaller datagrams, the fragments. And these fragments, if we look at the blue part corresponds to the header information, and the red parts are the payload data. That's the segment for the transport layer on the endpoint, or intended for the transport layer on the destination endpoint. So if we look at the payload area for each of these fragments, they add up, if you will. If you concatenate them, they comprise the first piece of the original datagram. The second piece is that second payload. The third and final piece is that third payload. And so it's broken up into smaller datagrams or fragments, and these fragments get forwarded along the MTU, or the link rather, associated with the smaller MTU, and then they're not assembled until they reach their destination. And so one might ask, well, how exactly is this managed? And that's what the discussion that we're going to carry forward entails. Okay, and they're reassembled. So continuing on, when we had the IP header, we talked about, in particular, among other things, these 3 fields. There's a 16-bit identifier, and that identifier is used to tag or identify the larger fragment that started out. And so each one of these pieces, these fragments, is a piece carved out of that larger MTU size datagram. And so you need some way of identifying which datagram it started out as when it was in its larger size. And so the other fields in particular are used for fragmentation and reassembly, or rather for fragmentation. There's a fragment offset that encodes where in the original payload a particular fragment's payload should be placed. And then the flags control whether or not it's a fragment or if it's the entire datagram in its entirety and when you reach the last fragment. Okay, so let's take a look at this. Well, we said before, and I won't focus on that, about the size of the header information for the transport layer, TCP, and the network layer, IP. So let's consider an example. Let's suppose you start out with a larger MTU size for a datagram for some particular link, and you send it to a second link, and that second link's MTU size is only 1,500 bytes. Let's consider what happens. Let me get my pen, change my pen color. Let's do a pen color of blue this time. Okay, I'll use my stylus here. And so we have the following scenario. We start out with an MTU of 4,000 bytes, and we hit a router, and we leave that router, the MTU is now 1,500 bytes. Now, in order to take that payload for that original datagram with a larger MTU, if we chop it up, we now need 3 datagrams of the smaller MTU size to hold that same payload data. So we have 20 bytes of header information. So that means the remaining payload for the larger MTU size is going to be 4,000 minus 20. That's going to be 3980. So that means we need to store 3980 bytes worth of information using an MTU size that's smaller. Now, given that 1,500 MTU size, each of the datagrams for the smaller MTU, well, that's 1,500. 20 of those 1,500 bytes are going to be header information. So that leaves 1,480 bytes of payload. So if you have 1,480 bytes of payload, that means you're going to need 3 of them in order to represent that original message, which is payload in the larger one of size 3980. So you're going to need 3 of them. Why 3 of them? Well, you have 1,480 bytes in the first one. So that's the first smaller fragment. Another 1,480 in the second one, 1,480. Now if we add these up, that's 0, 6, 1, that's 9, that's 2960. So we have 2960, we want to store 3980. So if we subtract 2960 from 3980, well, 3980 minus 2960, forgot I have it right at the bottom there, that's going to be 1020. So that means the first smaller fragment is going to store 1480. The second one is also going to store 1480 bytes. And the third one is going to store the remainder 1020. And we know it can store the full the remainder 1020 because it has a payload of size 1480. So what is also needed is this offset. And this offset tells us when we're reconstructing the original message, where do these pieces go? So here's our original message, and we're going to reconstruct it from all the pieces inside of these smaller datagrams. So we have the first small datagram, right? Let me just label that 1. We have the second small datagram. Let me label that 2. And then we have the third one. I don't know why I'm writing crookedly. Let me label that 3. So we said the first one is going to store 1480 bytes. So 1480 in here, 1480, and we have the 20 here. So this 1480 for the first one, it's going to be pasted in this first piece that's of size 1480. So 1480. This piece is going to just go right in there. And so if we look at the offset, the position in this larger payload, what we're reconstructing from the payload in the fragments, that position is going to start at 0. And we're going to write an offset of 0. And that needs to be carried in the fragment datagram because we need to know, where do I put this 1480? So now, if we look at the fragment field is 13, the offset field is 13 bytes, 13 bits rather, 13 bits long, right? If we go back to the previous slide, we see this fragment offset, we have these flags. These flags are 3 bits, and the fragment offset is 13 bits. Right? This entire width here, that's 16 bits, which is half of 32. 16 bits. And so because it's only 13 bits, your offset is going to represent a multiple of 8 bytes, right? So if you say some offset, that offset you can assume is not a sequential offset like offset 0, 1, 2, 3, 4, talking about the first, the 0th, the first, the second, third, fourth byte. It's going to be the 0th or first or second 8 byte distance. So if you have an offset of 0, well, it represents 0. If you have an offset of 1, it actually represents that offset of 1, dot, dot, dot. It represents a width of 8 bytes. Okay? All right. So let's take a look. We have here the first fragment. It stores 1480 as its payload, and it's the first fragment, so its piece is going to be in the first offset or the 0th offset when we reconstruct. Now the next one is going to start just after this 1480, or rather at the 1480. Because it's 0 based, it goes from 0 to 1479. And so the next, for a total of 1480 bytes, so the next offset is going to be representing the number of 8 byte units. I said 8 byte, not 8 bit, 8 byte units corresponding to 1480. And so I did a little math ahead of time. Well, if we take 8 byte units, 8, and we multiply by 185, that gives us our 1480. So that means the second fragment, it has 20 bytes of header information, and its 1480 payload, it's going to be pasted into the second section, starting at offset 185, because 185 is 1480 is the 185th 8 byte block. Okay, so we have that 1480. It'll come from that second IP datagram fragment, and then we have the third one. It has 20 bytes of header information, and the balance, which we calculated as 1020 bytes, is going to be pasted at this point right after the second 1480. Let me finish that 1480. Okay, so what is that endpoint of 1480? Well, if we take 1480 from the first one, 1480 from the second one, well, that position is 2960. It's 29, let me do it here, 2960. That's byte offset 2960. Now let's look at its offset in terms of 8 byte blocks. So if we take 370, multiply it by 8, that gives us 2960. Said conversely, 2960 divided by 8 byte blocks divided by 8 is 370. So that's going to be offset 370. Now if we look at the first fragment, its offset is 0. Okay, check. If we look at the second fragment, its offset is 185. Okay, check. If we look at the third and final fragment, its offset is 370. So that explains our offsets. But when we look at the fragmentation flags for the first fragment, for all the fragments except for the last one, the fragmentation flag or frag flag is set to 1. Then when we get to the last fragment, it indicates that it's the last fragment by turning off the fragmentation flag. Okay? And so in doing so, all of these 3 fragments are sent across the network. Now, of course, if you get to another MTU, and let's say that MTU is bigger, let's say this MTU is 4,000 bytes, it would still preserve these 3 smaller fragments, right? It doesn't reassemble at the router, it reassembles at the endpoint. But if you encountered another MTU, and let's say the MTU were smaller, let's say this MTU was, say, 1,000, then you chop this one, first one, up into 2, because you can represent that payload using 2. The second one, you would chop that up into 2 fragments, and the third one, you chop that up into 2 fragments. So now we'd have 6 fragments instead of 3. And all of this does not get reassembled until you get to the destination endpoint, your destination. Okay? All right. So it will subdivide and make fragments smaller, but it will not increase them in size. And they're propagated through the network and reassembled at the endpoint. And it kind of makes sense, right? If you're going to reassemble them, do it at the endpoint, because why chop it up into smaller pieces only to reassemble it, only to chop it back again into smaller pieces? And you're also keeping the complexity at the endpoint, which is a very important tenet that you see in computer networking. Keep complexity at the endpoints. Okay, so we have this length field, 1480 bytes. Our offset here is 185 for the second fragment, and our offset for the third fragment is 370. All right, so let's take a look at the addressing for Internet Protocol. An IP address is a 32-bit quantity, and this 32-bit quantity is represented as 4 8-bit numbers. Now, sometimes you'll see this 8-bit number represented in hexadecimal, but usually it's represented in decimal. And so each 8-bit number, as 8-bit number, you can have a value from 0 at the low end for all zeros to 255, which is all ones. And when you take this 32-bit number, you describe it as a so-called dotted quad, right? You have 4 numbers in decimal, and each one of these 4 decimal numbers can be between 0 and 255, and it represents the decimal equivalent of that base 2 or binary number, representing each of the 8 bits that collectively comprise your 32-bit address. And so you have a 32-bit address corresponding to a host, and more correctly, it's a network card or network interface. Now, a router is nothing more than a specialized type of host that has more than one interface. And so here we have a network, and you'll notice here we have networks that have names that are very similar to one another in terms of these addresses. So there's 223.1.1.1, this first machine or host or interface on this network on the left. There's 223.1.1.2, 223.1.1.3, and 223.1.1.4. Now this router, you'll notice, for every computer on this upper left network, the router shares an interface that it can use to reach each of these computers. The interface is this connection between the host or router and the physical link. And that physical link can be fiber optic, it can be coaxial cable, it can be category 5 or copper wire, it can be wireless. And routers always have multiple interfaces, which I think I said already, and you have an IP address associated with each interface. So let's take a look at this first IP address, 223.1.1.1. If we decompose this in binary, well, this string pattern is 223. Then we have 1, which is all zeros and a 1, all zeros and a 1, all zeros and a 1. Okay, so how are these interfaces actually connected? Well, when we talk about the link layer, we'll learn more about that. But we can just assume at first approximation at this juncture in the course that they're connected and they can communicate with one another if they're sharing some area or local area, we'll call it that. So there are some devices called switches, and a switch operates on the physical layer as well as operates or implements the link layer. And sometimes this is called the layer 2 device. And so in reality, a switch is what connects these hosts together in the local area. And this can be something like wireless, it can be wired, lots of ways to do this. And so that's the most I'll say about layer 2 devices. We're going to focus on the network interface and the relationship among all the machines that are in the same so-called local area. Okay, so you also have wireless interfaces, and these wireless interfaces act like wireless switches. In reality, all of the devices on the same local wireless area network are in broadcast range from one another. So that means literally for the antenna for this machine at address 223.1.3.1, all of those machines in local area, they can receive wireless signals among one another, right? They're in broadcast radius. That puts them on the same local area network, or local area. Now, of course, one of the observations that you make is that you have some interfaces. They're quote unquote directly connected to one another, and other interfaces aren't directly connected to one another. If you want to send a message from, say, this host, let's call it host A, to some host B, you can't send it directly. You're not in the same local area. You have to send it to the router in your local area, which then forwards it to that destination. And the router can do that because it shares a local area with the destination machine. And certainly, as we've studied before, you look up the destination address in a lookup table, and it says output it out this output port, and it makes its way to destination 223.1.2.1. Okay, so the IP address is not arbitrary. We can decompose this as a binary number, but when we do that, we like to associate the higher order, most significant bits with the so-called network, and the lower order, the least significant bits, are associated with the host on that network. So if we take, for example, this number, you'll notice that all of the hosts on this upper left-hand network have the same most significant bits, if you were to decompose this into binary, of 223.1.1.1. Now that's going to be the network, and we can identify that network using that number, that address. It's called the network address, or the subnet. Now this is network 223.1.1, and this last part describes the host. So we identify the network using the subnet, the high order part of this address, and the host is the low order part. So here we're using the first 24 bits out of 33 to identify this network, and then the last 8 bits to identify the host. So this is the first host on the 223.1.1 network. This is the second host on the 223.1.1 network. This is the third host on the 223.1.1 network. And lastly, this interface with the router is the fourth host, or fourth network interface card on the 223.1.1 network. If you cast your attention onto this other subnet or other network, well, this is the 223.1.3 network. It's different from the 223.1.1 network. The 223.1.3 network has a number of hosts. This is the first host on the 223.1.3 network. This is the second host on the 223.1.3 network. And this is the 27th host, the interface to the network card on the router on that network. It's the 27th host on 223.1.3 network. Now, when you assign these host numbers, they don't have to be sequential. They just have to be unique. So when you want to send a message from host A here, let's say if you want to send it to host C down here, calling it host C, well, you can't send it directly because you're not on the same network. So you send it to your local router. That router sees the destination address, looks up in the lookup table, and then sends it out onto the network. It gets picked up and ultimately delivered to host C on the 223.1.3 network, which is host 1 on that network. So in this diagram, we have 3 subnets. This is the first subnet, the 223.1.1 network. This is the second subnet, the 221.1.2 network. And lastly, down below, we have the third subnet, the 223.1.3 network. And so that's how we design the address. That's the interpretation of the meaning of the address. There's the network address, the subnet, and then there's the host part. And you notice here, because we have 8 bits as the host part, we can have as many as 2 to the 8 power many hosts, which is 256 different hosts, going from 223.1.0 up through 223.1.1.255, right? So here we have subnets, and you might be asking, well, what's actually a subnet? A subnet has all the device interfaces that contain the same subnet part of the IP address. So here, all of these devices in this upper left subnet, they all share the same network address or subnet address, 223.1.1. Likewise, for this subnet on the upper right, all of the interfaces on that subnet share the same subnet address or network address, 223.1.2. And similarly for this third one. And so device interfaces with the same subnet part of the IP address, they're on the same subnet. And moreover, if you're on the same subnet, you can physically reach or send messages or interact with one another without the need of a router. So what does that mean for wireless? It means that this host can send a signal, wireless energy, and this host is in its broadcast radius, and it picks up that information, and it can reciprocate, sending wireless energy to the other machine and communicating. Same thing with the router. They can communicate with the router. They're in broadcast radius. What it means on a wired network is that you have a device called a switch, and into that switch is plugged in the Ethernet cable for all the hosts, and they can now maintain an electrical connection, pass signal or message data to one another without the need of a router, right? So that's what it means to be on the same local area network, the same network. You can physically reach each other without an intervening router. Now, sometimes in your wireless interface on your laptops, sometimes some operating systems expose a setting that says, I want to go in infrastructure mode or ad hoc mode. With ad hoc mode, what you're doing is you're sending messages directly to other machines on the same subnet or in broadcast radius. Okay, so one of the recipes for how you define and how you describe subnets is to detach each interface from its host or router, and when you do so, you create these islands of connectivity. And each island of connectivity, things that can reach one another directly without going through a router, that's called a subnet. So in this diagram, we have 1, 2, 3 subnets, left, right, and bottom. And when you depict a subnet, you have the address of that subnet, but you have this other thing following, /24. Now what that number represents, that's the number of uppermost bits that are used to define the subnet. So here, if you have 223.1.1.0, well, this is 8 bits, the decimal representation of an 8-bit number, 8-bit. This is 8 bits. This is also 8 bits, right? And so you add 8, 8, and 8, that's a total of 24 bits. So now that means that for whatever the decimal representation is for these 4 8-bit numbers, the uppermost 24 bits is going to be the subnet mask. Now, of course, you have a 32-bit address. If you have a 32-bit address, you draw 32 bits, and you're using 24 of them for the subnet, well, that leaves 8 bits for the host. So in that case, this subnet can have as many as 2 to the 8 power, which is 256 different hosts. After that, you can no longer have a unique host identifier, i.e. a unique address. So here we have the 223.1.1.0 network, and a subnet mask is 24, and you need that subnet mask in order to identify the network. And in fact, when you buy blocks of IP addresses, you're given this quantity. That's the subnet address or the network address. And it's up to you, entirely under your control, what you assign as the host number, because you control the hosts that are on your network. Okay, so here we have the 223.1.2.0 subnet 24 subnet. And we also likewise in the bottom we have the network 223.1.3.0 subnet mask 24. So each isolated network is called a subnet. All right, so here's a question for you, and I encourage you to push pause. How many subnets are in this diagram? So I'll just wait for a moment. Please push pause, think about it, and come up with your answer. Okay, so if we look at the top, well, we have 223.1.1.0 subnet mask 24. So that's one subnet, the 223.1.1 network. We also here have the 223.1.9 network. So that's 223.1.9.0 subnet mask 24, right? And just because you don't have hosts attached, it doesn't mean you're not a network. All a network is an island of connectivity. So here we have the network interface card for that router, network interface card for that router, and no hosts. Well, it's two network interfaces with the same subnet mask. So this is a subnet, the 223.1.9 subnet. Okay, so if you wanted to, at some point, you could say, okay, well, let me input a switch here, and then let me hang a machine off of there. And now, you could give this an IP address 223.1.9, and maybe you call this host number 3, because host number 1 is there, interface number 2, and host number 3 is there too, right? And so it doesn't have to have a host present in order to be a subnet. It's a very technical definition. So that's one, the 223.1.1.0. This is 2, second subnet. Okay, we have that. Now this is the third subnet, right? That's the 223.1.7.0 subnet 24. All right, that has 2 hosts, 2 interfaces. This is another one, so that's 4. It's the 223.1.8 network. This is number 5. It's the 223.1.2 network. And then we also finally have number 6, the 6th network, 223.1.3. Okay? So we have a total, the answer, we have 6. Okay. So how do we do addressing? Now, in the old days of networking, we had 3 classes of network, and the classes of network were defined based on the number of hosts you can have on that subnet. You had a so-called Class A, Class B, Class C networks, and you could also have a Class D, it was just one, but you had these different types of networks. And what happened is that they started running out of IP addresses, because in the beginning it wasn't envisioned that people would have a number of machines on the network. And so what this CIDRized notation does, it takes into consideration the subnet when it's doing the routing, because essentially all you care about is not the particular address, but really, if you think about it, the block of addresses that a particular singular IP address belongs to. So you have the subnet portion of address, and the nice thing about CIDRized notation is you can have a subnet of arbitrary length, instead of handing out networks that had a subnet that was 8 bits long, or 16 bits long, or 24 bits long, right? You could have arbitrary, like 23 bits, 27 bits, 29 bits, and so forth. And so that allowed you to more efficiently hand out blocks of addresses, because in the beginning or early days, you could only hand out blocks that were 8, 16, 24 bits, and so forth for your subnet. And so in doing so, well, you still have the subnet part, and in this example, you have 200, so this is 200 in binary. You have 23, right, 16, and 0. And the subnet mask is 23 bits long. So this is 8, 16, 18, 20, 21, 22, 23, and that leaves a total of 9 bits. 23 and 9 is 32, 9 bits left for the host part. Now, of course, if you subscribed or purchased this block of addresses, you could then turn around and make subnets maybe including these bits, and then every subnetwork would have only 8 machines on it. And so the CIDRized notation or CIDRized routing allows you to arbitrarily subdivide blocks of addresses by tinkering with the subnet mask. Okay, so how exactly do you get an IP address? Now, many of you, you come to, well, when we're at the department, you go to the department, or maybe you have it set up on your home router, particularly for mobile devices. You open it up, and then all of a sudden it connects to the network, and you can plug and play, just off and running, exchanging packets, watching Netflix, watching Blackboard, and all that other good stuff. There's a protocol called Dynamic Host Configuration Protocol, DHCP. And this is a protocol used to bootstrap the assignment of IP addresses to machines that join the network. And not only does it give you IP addresses, it also gives you other useful configuration bits of information, such as the default gateway, the first hop router that you need in order to send data off the network or get data from your network, as well as other types of things, configuration type things. Now, oddly enough, I remember early in my career, when I worked at Sun Microsystems, I had the great good fortune to work with someone named Mike Carney, who was on the Internet Engineering Task Force, and he actually headed up the subcommittee that created DHCP. And so, Mike, if you hear this, hope everything's going well. So Mike Carney, when I was at Sun Microsystems, Sun Microsystems was purchased by Oracle, and Sun Microsystems was a casualty of the .com bust. But nonetheless, DHCP is a plug-and-play mechanism, and it actually derives its existence from something called bootp. Anyway, so how does it work? Well, the goal is to allow a host to dynamically obtain its IP address from a network server when it joins the network. And this is lease-based, it's not exclusive, because you might leave the network. And so typically how the system works is you request an IP address in order to connect and push packets to and get packets from the network. And it's leased. And if you don't renew the lease, you lose that IP address. If you do renew the lease, well, you continue to use that IP address. Now, of course, this allows you very easily to share networks. And in fact, it allows you to get away with having fewer IP addresses than having one IP address per user. Now, of course, there are other enterprise features that people have with DHCP, so-called DHCP custom variables or extensions that allow you to do things like assign where is my cloud storage server, or where is my shared network drive, and so forth. So there's all sorts of things that you can do, quite interesting configuration-wise with DHCP. But we're just going to talk about the basic, namely things like your IP address and your default gateway, and also things like name server, things that are important to configure if you're going to have internet connectivity. So what does it do? Well, DHCP, the connecting host, broadcasts a discovery message. And the reason why it broadcasts is because at the beginning, when you join the network, you don't have an IP address, so you cannot be uniquely identified. For every network, there's a so-called broadcast address. And if you send a datagram to this broadcast address, it's going to propagate that to every host on the network. Now, I said on the network, not across the internet. And so this discovery message is broadcast, and the DHCP server is one of the things that receives this broadcast. Now, it's a controversial thing to forward broadcasts across a router because you can end up flooding a network and wreaking a lot of havoc. But nonetheless, the DHCP server is on the network, and it hears or receives this broadcast. So then, as a result of receiving the broadcast, it broadcasts back an offer. It says, hey, I have an available IP address that no one has reserved, and no one's currently executing a lease on it. This is what that IP address is. So then you receive that broadcast and you respond to it and say, okay, well, let me reserve this. And the DHCP server gets this broadcast back reservation, and it sends back an acknowledgement. And once it sends back the acknowledgement, you, the host, know that, okay, let me install this IP address. That's now my IP address. And after that, you can now use a real IP address instead of using broadcast. So some things that need to happen is that when you're doing this broadcast and making this offer, right, that broadcast is going to be, so here's your host, and that host is on the same network. Say it's connected to a switch, and there are some other machines, another host, and here's your DHCP server, and that's the switch, DHCP, and then for good measure, it's also connected to a router, right? And that router can forward packets off the network to the internet. That's supposed to be a cloud. All right, so you send a broadcast, and when you send that broadcast, that's the discover message. That discover message is propagated throughout the network. It's broadcast. So the DHCP server gets it. Now it needs to identify which discovery message it is. So there's a unique identifier that says, okay, which request is this? So it gets that discovery message, discovery, and then it broadcasts out its response. It gets flooded across the network. And you, the host, say, aha, I received an offer, and that offer had the same ID, let's call that X, as my discovery message. So I know that this broadcast that was sent is a response to my request. So then you make another round of broadcasting the reservation, that's the DHCP request message, and then you get back an ACK. And when you get back that ACK, it means the DHCP server has reserved, if you will, a certain IP address that it had offered in the original response back. Okay? All right. So let's take a look at this. We have an arriving DHCP client, and it needs an address in order to participate as a member of this local area network. Now, certainly that address being offered is going to be a host address that's on the 223.1.2 network. So this arriving host comes in, and it sends a broadcast message sort of shouting out the window, hey, anybody out there for DHCP? Okay. And so this message has a source IP, it has a source IP address of all zeros. And the reason it's all zeros is because that client does not have an IP address. So it just chooses all zeros, port 68. So the destination address, that's the broadcast address. And you'll notice this broadcast address is 255, 255, 255, 255. All the so-called dotted quad numbers are 255, which consequently in binary is all ones. And it's also port 67. So here, this destination address means that you're going to flood the network. Everyone in your local area network is going to receive this message. Now, of course, you have to be listening on port 67 in order to get this message. The DHCP server is listening on port 67. And they also have this thing called YIAddr, your internet address, and a transaction ID. That ID is the unique identifier for the request that's broadcasted by this client. So then what happens, the DHCP server gets it, and it sends back via broadcast, I'm a DHCP server, and here's an address that's free and available that you can use. No one else is using this. And so this DHCP server is managing a block or range of addresses, and it says, okay, there are no leases, no reservations on this one. I'm going to offer it to you. Here's an IP address you can use. So the source address, the DHCP server, it has an address, and it's at port 67. And the destination is going to be 255 because it doesn't know who that client was by its IP address. All it knows is somebody broadcasted it. So it broadcasts by sending to this destination address all 255, 255, 255, 255, and it uses port number 68. Now, of course, the source port was 68 for this client. So that client is running a process that's listening in on port 68, and it's getting this broadcast traffic because it's sent to everyone on the local area network on that 223.1.2 network. Okay? So the address, IP address that was offered by the DHCP server is this one, 223.1.2.4. So it says, I'm going to offer you the address for host 4. I will call you host 4 on the 223.1.2 network. And here's the transaction ID. So by matching up this transaction ID, 654, it knows, hey, that's the broadcasted response to my request. And the lease is going to be 3,600 seconds. That's the longest I'll let you use it, and you have to explicitly renew it in order to continue using this IP address. Okay, so then the arriving client says, okay, well, I'll take it. Now at that point, it hasn't yet installed that address. And the reason it hasn't installed that address is because it has not yet been reserved by the DHCP server. So this, I'll take it, I agree, handshake, a deal is sealed, that message from the client is also broadcast. So what does it do? Okay, again, the source IP is all zeros, the port number 68, the destination address is that broadcast destination address, and again, it's port 67, right? This DHCP server is listening in on port 67. So it gets that, and it says your internet address, because it's saying, when I say I'll take it, well, the DHCP server needs to know, or what is it you're trying to take? Now, the last interaction, right, you see, was transaction ID 654. It now has a new transaction ID because it wants to match up the response with this request. So it's transaction ID now 655. So then the DHCP server, in this period of time, it reserves the IP address 223.1.2.4, and it broadcasts back its response. And why does it broadcast? Because at this juncture, still the arriving client does not yet have an IP address. So this broadcast message, the source IP, well, that's the source address of the DHCP server, port number 67, the source port number, okay. The destination address is broadcast, port 68. And again, recall the arriving client is listening in on port 68. It gets this datagram because it's broadcast, it's sent to every machine on the local area network. Okay, and it has this address, okay, and here's the transaction ID. So that way the client knows that this response that was broadcasted is the response to this request to reserve what was offered in the last round trip time. And so the lifetime is 3,600 seconds. And then at this juncture, the client says, okay, now I'm going to set my IP address to be 223.1.2. So that's the 223.1.2 network. The host part is now 4. And that after that, any message that goes across, the source IP address is going to be this 223.1.2.4. Okay? All right. So DHCP can return more than just the allocated IP address. It can also assign the first hop router. Now, the reason why that's important is, let's say we're going to draw a subset of a network. That's a switch, right? A switch is square, a router is circular. And we have host A. Let's say that's a new client that's coming to the network, A. And then let's say you have another host, B, connected into the switch. Also connected into the switch is some router, and that router is going to be the first hop router that you will use to get your data off either to the rest of the network, or maybe it's into the internet. Okay, so in order to actually use the network, what do you need? Well, you need an IP address, so you get your IP address through DHCP, but other so-called variables that you can set are things like your default gateway. Now, your default gateway is the IP address of the router, which is the first hop router on your network. And the reason why you need that default gateway is because anytime you want to send data off network to some other host across the internet, maybe there's some other router here and there's some other host, you want to make sure that you're going through a router, because without a router, you can't send datagrams to another network. That's the goal, that's the function of a router, the whole purpose of a router. Without a router, you can only send to other machines in your local area network. With a router, you can send outside the network. And for that reason, if you want to use other services on the wide area outside of your local area, right, you want to make sure that you have the address of the router you need to get your data off of your subnet. And that's called the default gateway, and you need its IP address. So that's another thing that can be configured plug and play using DHCP, not just the IP address. And it works similarly, not just the offer, but it also includes additional variables as payload on this acknowledgement message. So we have the default gateway in addition to the IP address. Another thing you need is the DNS, right? So maybe you have connected to your network through a switch. You have your local DNS. Now, your local DNS knows how to connect to the root DNS, as we had discussed. It knows how to connect to the top-level domain DNS, and it knows how to forward and connect to maybe the authoritative DNS for some organization you're interested in. And whether it's iterative lookup or recursive lookup, it doesn't matter for our conversation. And so what you need also, it has an IP address for the local network, your local DNS. You also need the IP address of your local DNS. And you need that because you might want to type in www.google.com or gaia.umass.edu. Well, in order to resolve that name into an address, you need the IP address of your local DNS to forward that message to it, and then it engages with the other DNSs in the hierarchy to resolve that into an IP address for the destination. So you also need the local DNS. You also need the network mask, because without the network mask, if you have an IP address, in this case 223.1.2.4, 223.1.2.4, without the network mask, you don't know what part of this 32-bit number, as described by 4 base 10 numbers, you don't know which is the network address and which is the host address. So you also need the net mask, and it'll typically be, well, not typically, it'll be sent to you as a net mask, and it'll have a number like 24, right? And you need that in order to know what is your network and what is the host number, okay? And that helps with the routing. All right, so DHCP can return more than just the IP address. It can return the default gateway or first hop router's IP address. It can return the IP address of the name server, your local DNS, or as well as the network mask and all sorts of other things. And I leave it to you to Google search DHCP protocol to learn more about the other types of variables DHCP can set. And Mike Carney's name you'll see is up there quite a bit. All right, so here's an example with DHCP. You have a router, and that router box, the thing you'd buy from Best Buy for $100, $200, has DHCP server built into it. And so from this class, you learned that that box you buy from Best Buy, it's not just a router. It's running DHCP as well as the routing function. So you have this router and it has DHCP server built into it. You have an Ethernet switch here attached to your machine, and you attach your machine to the network, and this DHCP message makes its way down the stack, and it's using UDP because if it doesn't get there, you can just resend the DHCP request. So it comes down the stack, is encapsulated in UDP, encapsulated with IP header, and it's sent out through the link layer on Ethernet, and it is broadcast. So it's broadcast, it makes its way across the switch to the other machines on the network, one of which is the DHCP server. The DHCP server gets this message, sends it up the stack, stripping off the header information that's meaningful at each place in the stack. It takes that DHCP request that's broadcast, and it responds back with the offer, which is also broadcast. So in the beginning, this Ethernet frame is sent to this address. Now you'll notice this address is not 255, 255, 255, 255, 255. It's now FFFFFF, right? All these Fs. Now, in hexadecimal base 16, that's often how you write these addresses. And base 16 just takes every 4 bits. So if you have 255, right, that's nothing more than 8 1 bits, 1, 2, 3, 4. And with hexadecimal, you separate out these binary digits in groups of 4. And with 4 bits, you can represent 16 alternatives. And so 255 is nothing more, if that's 1, 2, 3, 4, 5, 6, 7, 8, that's F, F, right? In hexadecimal, you depict numbers as 0, 1, 2, 3, up to 9. And when you get to 10, right, you use the alphabetic character A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. 15 is 1111, 1111. And so if you have these 4 digits in hex, you can represent 2 to the 4 is 16, right? So 1111 is 15. So that's F, which is 15, F, right? The next 255, right, is 1111, 1111. The next one is 1111, 1111, and then lastly 1111, 1111. We have F, 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 and lastly F, F. Okay? All right. So that's the address for broadcast. It's all Fs in hexadecimal. So we broadcast that message. It makes its way to the DHCP server. It passes that message off the network, up the stack, strips off the headers, and then responds to it via broadcast. So it broadcasts it back to the network, and that's its offer. And because it's broadcast, it makes its way to every host on the network through the switch, one of which is the requesting host. It gets that, strips off the headers, makes its way up the stack, and then it sends reserves. It does that reserve, and it gets this DHCP response after it does the allocation. So there are 2 rounds. There's the request that goes in the forward direction, that's broadcast. It makes the offer. It then does the reserve, and then it does the acknowledgement, right? So this is the first round trip, and this is the second round trip, and it's all via broadcast. So once this reservation happens and the acknowledgement occurs, this client knows its IP address for itself. It knows the IP address of the gateway, the default gateway, which is the first hop router. It also knows the address of the DNS, and it also knows the net mask. And the example we've been carrying, that net mask is 24. Okay, so all of this happens in maybe a second or a fraction of a second, simply by plugging in your laptop or desktop to the network. Okay, so this text is an actual output from Wireshark of DHCP. Sometimes you might select boot P. Boot P was a precursor of DHCP. And so you have message boot request. Here's the client IP address. So it's all zeros. Your client IP, next server. You have the MAC address. We'll talk about that with link layer. It uniquely identifies the network card on the local area network. You don't have a server. It's a message, a DHCP request type. And then you have a bunch of other pieces of information. So now, when you get the reply, boot reply, well, here's a transaction ID, right? And you notice this transaction ID in hexadecimal 0x, 6B3A11B7, 6B3A11B7. So this is the response to this boot request. And it says your internet address, right? Client IP address. Let's see. Your internet address is all zeros. That's the response. And then next server address. Okay. That's the next hop router. And it has a bunch of information. And then it's an acknowledgement. So this ACK here, when you get the acknowledgement, here we have the default gateway. That's your router. The subnet mask, this is a 24-bit subnet mask. Either subnet mask is given as a number, like 24, how many bits. Sometimes the subnet mask is given as a a decimal dotted quad. And in this particular case, your subnet mask, I know it's 24 because if you take each one of these numbers, decompose it into binary, it's 1111, 1111, that's 8 ones, another 8 ones, and another 8 ones. That's a total of 24 1 bits if you have 255, 255, 255. And we also have the ACK type and the DNS. We have the IP addresses of the DNS server, and then the domain name itself is set. That's an additional piece of information, another variable added to configure the host. So this is an example Wireshark. You will have an assignment in the future. Have to figure out how to do that as a pure remote. Maybe I'll go out and measure stuff. Haven't really figured it out yet. We'll get to that when the time comes to do our Wireshark assignment for the network layer. A lot of people have fun with it. So IP addresses. How do you get an IP address? You generally, when you go to an internet service provider, you request an IP address, and what you're given is a subnet. And that subnet summarizes a block of IP addresses. Now, typically, what you're getting when you rent or subscribe to a block of IP addresses is some internet service provider has a larger block of IP addresses, and they're just carving out of their address block a little bit for you, right? And so here we have an example, an internet service provider. This is 200 in decimal. We have 23. 16, 0, and the subnet mask for the ISP is 20, right? So we have 8, 16, and 17, 18, 19, 20. So the subnet mask chops off here. So this is the subnet, and this is the host part, host. So if the subnet mask is the uppermost 20 bits, that means the host part 32 minus 20 is 12 bits. So that means you can have, for this internet service provider, they can have a total of 2 to the 12 many machines on their network. So let's say this service provider, it sold blocks of IP addresses to customers. And let's say it sold them to 8 customers. Well, if you're going to sell them to 8 customers, you have to give out a subnet mask that's carved out of yours. And so to represent 8 different subnets or blocks of addresses from your range of addresses, well, you're going to use 3 bits, right? Because 2 to the 3 is 8. So now what you do is any packet that has a destination address with this subnet, it's going to come to your router. Now it's up to your router to decide, based on these next 3 bits, where to push that traffic. And so what you can do is arbitrarily divide up the address space that you own, right? And so that means when you hand out these blocks of address, if you're going to hand them out to 8 different people, you might divide them up into 8 equal-sized pieces. So that means for each of your customers, you're now going to have a subnet for those customers carved out of yours. So instead of 20, you're going to make it 23 is a subnet mask. So that means these extra 3 bits are going to be the subnet for your customers, right? And that leaves 23, 9 bits, 9 bits that each one of your customers can have for the host part. So that means 2 to the 9, right? So 2 to the 8 is 255, so 256, so that's 512. 512 machines total on each of these subnets that you've carved out of your address space. So the first organization, their subnet is going to be identified as the 0 subnet out of yours. So these 3 bits, you notice it's all zeros, and the subnet mask is 23. If the subnet mask is 23, it refers to up to including this portion. So the next one, the first one's 000, the next one is 001, and then 010 for 0, 1, 2, 3, and so forth. So now you're going to represent these using binary numbers for that third 8-bit representation, and you're going to set the subnet mask appropriately for that subnet portion for those IP addresses carved out of your own address space. So here we have 223.16.0, subnet mask of 23, 223.18.0. Now this is really important. If we go to 18, that corresponds to 001 in these 3 bits. So even though it's that next part that's carved out, you have to make sure that it lines up with the right subnet. Okay? So now next we have 20, right? So 010, right? For this subnet, that 010, if we take this portion and we add that portion, that's 1, 2, 4. 4 plus 16 is 20. So here we write 20, and the subnet mask we pay attention to is those 23 bits, which corresponds to all this portion going across, the uppermost 23 bits. And so lastly, that last subnet, these are going to be all ones, right? Because if we have those 3 bits, we go through all the patterns for how we make those extra 3 bits for that larger subnet mask. How many different ways can we make it unique? We have 8 different ways. So here, this number is 30, right? We have, see, we have 1, 2, 2 plus 4 is 6, 6 plus 8 is 14, 14 plus 16, that's 30, right? So that would be 200.23.30.0 subnet mask 23. So our subnet mask uppermost bits here, 23 bits, right? Going for the uppermost here from left to right. Okay. So now, if we have hierarchical addressing, this idea of dividing network addresses into subnet parts, and we can arbitrarily carve up those subnets into smaller subnets, smaller meaning that they have a smaller number of hosts because the host part of that subnet, of that address is smaller. Now you can address things hierarchically. And the benefit is illustrated, it's in the book. Suppose you have an organization called Fly-by-Night Internet Service Provider, and you advertise to the routers, gateway routers on the other side of the internet, hey, every time you have an address that has the following subnet, 200.23.16.0 with a mask of 20, send that data to me. Now, you send that data to you, you know from advertisements from gateways for each one of your customers, well, I manage all the addresses with 200.23.16.0 subnet mask 23. So that means all that data that can go to any one of these organizations is going to be sent in aggregate to Fly-by-Night ISP, and Fly-by-Night ISP is going to send that data out the correct output port because the destination address is going to be different based on that block of 512 IP addresses identified by these larger or these smaller subnets. It's a smaller subnet because it has a smaller number of hosts. It's a larger subnet mask because the mask is a larger number of bits. So in essence, this occupies the first 512 of addresses, the next 512, the next 512, the next 512, and you have 8 of them. Okay. So what happens then? We have another ISP. Almost slipped my mind. Another ISP. ISPs are us. And it says, okay, well, I'm going to manage a different block of addresses. Send me anything with addresses that begin 199.310.0 subnet mask 16. So that means this can have a total of 2 to the 16 many hosts. That's a decent amount of hosts. Okay, so all data in this block of addresses gets sent there, and it's subdivided by Fly-by-Night ISP to one of its customers based on the block of addresses. It's more and more specific as you get closer to the organizations. And here you have a different set of addresses. Now, of course, an organization might move. You might change ISPs. Maybe you're on Sprint and you want to switch to Verizon as a customer. And you want to bring your IP addresses with you. Well, you're assigned IP addresses by a different organization, so they're yours as long as you keep paying the subscription. So if you move ISPs, you still keep your IP addresses. So what happens if this for some organization 1, it has the block for subnet 200.23.18.0, subnet mask 23, and let's say it physically moves to ISPs are us. Now ISPs are us, it had the following block of addresses: 199.31.0.0, subnet mask 16. Now if it moves, you want to do something a little bit different. Now, fly-by-night ISP has not changed with the advertisements it sends out to the gateway on the other side of the internet. It has not changed in terms of the advertisement it makes. But what has changed is that now that Organization 1 has joined ISPs are us, it takes this advertisement for a block of addresses and it aggregates that into its advertisement to announce that, okay, not only do I manage this block of addresses, I also manage that block of addresses. Now, of course, this block of addresses logically fits inside of the 200.23.16.0 mask 20 block of addresses, because that's where they started from. But recall when we talked about this forwarding table, it does what's called longest prefix matching. And so here, because the subnet is bigger, it has a longer prefix. And that means if you have an address and that address is in this block, it's always going to send it down to ISPs are us if it matches this, because this sits within that block of addresses, but this advertisement matches a larger number of bits. The subnet mask is bigger. So that means that it will always send down here if it belongs to this block of addresses, because this match for this one matches a larger number of bits, 23 bits for the subnet, versus this one matches only 20 bits. And so you can now pick up and move organizations arbitrarily, and then when you join an ISP, you in your routers, you're advertising the presence of your block of addresses that gets pushed out by the gateway router for your ISP to the internet's gateway router. Okay? And so even though logically your block of addresses falls within somebody's range of addresses, because of this longest prefix matching, it'll always get to the right destination regardless of where it is. Okay? All right. And so how do you get a block of addresses? You go to the Internet Corporation for Assigned Names and Numbers, ICANN, and this is the organization that acts as the arbiter of IP addresses. They manage the DNS instances, and they also assign domain names and resolve disputes. Now, this is a tricky thing, this managing of disputes. Let's say your last name is McDonald, and you wanted to have, say, a painting shop, or you wanted to, print t-shirts, or maybe you wanted to have IT consulting, and you wanted to call it McDonald's IT Consulting, and you wanted to buy McDonald's.it, right? There'd be a problem there, because McDonald's, the burger restaurant, fast food place, they're going to have a problem with you buying McDonald's.it. I'm pretty sure McDonald's already owns McDonald's.it. But nonetheless, anytime there's a dispute over who should have a domain name, this organization acts as the arbiter to resolve them. So if theoretically, if your business has nothing to do with food or restaurants, you might be able to win this dispute if you have enough money for lawyers. All right, but anyways, nonetheless, ICANN is the one who assigns and manages these blocks of addresses, and you pay for it. And as long as you continue the subscription, it's yours. And if you change internet service providers, it moves with you. And longest prefix matching allows your messages to get to you correctly, regardless of in which service provider you locate. Okay, so with that, I'm going to stop here.